Hi, my name is Katie, and I am joined by Elena and Joseph. Richland Creek, a stream located within McCabe Park and extremely close to a golf course, was inferred to have poor water quality due to its close proximity to the effects of urbanization. In contrast, the Little Harpeth, a stream located within Percy Warner Park, was inferred to have better water quality due to its assumed distance from pollutants and the effects of urbanization. Noting rivers' impacts on ecosystems and how poor water quality can affect surrounding communities and biodiversity, we compared water quality metrics from the Little Harpeth and Richland Creek to advise communities in the future on opportunities for remediation to promote healthier streams.
We collected weekly water samples from early February through early April, as well as 2 late spring dates from 2 locations, Site 5 in Richland Creek and Site 11 in Percy Warner Park. Water quality metrics were measured on-site using probes, including flow, dissolved oxygen, conductivity, temperature, and pH. Additionally, we conducted lab tests for nitrogenous compounds, as well as salinity and turbidity. We also recorded site conditions using modified USDA criteria. Lastly, we conducted a variety of statistical analyses, including a principal components analysis, ANCOVAs, and ANOVAs for each water quality metric. These metrics were also compared to available EPA standards.
To begin, the principal component analysis in Figure 6 represents a breakdown of all collected water quality metrics and additional variables, including date, into 2 primary components. As you can see on the bottom half of the graph, Richland Creek states are clustered, indicating a collective similarity among data points specific to the river. On the other hand, Little Harpeth's data points have greater distance between them, and some dates from the same month are not together, highlighting some difference within the first and second components. The demonstrated division among components could be attributed to seasonality and the persistent fluctuation of environmental factors, reaffirming the need for consistent and frequent data collection in the environmental science research field. More regular field observations and data collection offer opportunities to further definitively assess the health of a body of water and noteworthy fluctuations in metrics, laying the groundwork for our concluded suggestion to professional water quality researchers regarding collection frequency.
We then compared the average nitrate concentration between Richland Creek and Little Harpeth, calculated from our data. We found that Richland Creek had a calculated average of 11.1 milligrams per liter, and that Little Harpeth had an average of 7.6 milligrams per liter. While the p-value for a conducted ANOVA statistical analysis was not significant, when compared to currently available state standards, Richland Creek's average nitrate level exceeds the 10 milligrams per liter concentration safely allowed in rivers for fishing and recreational use.
Additionally, in Figure 8, you can see an analysis of covariance of flow versus nitrate. The shown trend demonstrates that flow has a significant impact on nitrate. Interestingly, Richland Creek has a stronger trend of nitrate increasing as flow increases in comparison to Little Harpeth. When it floods or stormwater drains into the creek, the fertilizer from the golf course leaks into the stream and increases the nitrate values. This finding reaffirms how the golf course's proximity to Richland Creek may be negatively impacting water quality and how the exceeding nitrate levels remain relevant despite a lack of statistical significance.
Further, because high nitrate and high phosphate values are good indicators of eutrophication, Figure 9 compares nitrate and phosphate. Typically, nitrate and phosphate have a direct relationship. However, our data demonstrates that Little Harpeth tends to have consistent nitrate values despite phosphate increasing. The demonstrated trend in the Little Harpeth could be attributed to the decreased observed amount of nitrate present. Additionally, we observed greater algal cover in the Little Harpeth, thus the algae present likely contributed to the decrease in nitrate via consumption. Furthermore, phosphate often remains locked in sediment, while nitrate can be released through air or water movement, further offering potential explanation for the lower nitrate level in the Little Harpeth.
In conclusion, despite the few observed differences and contrary to our expectations, the results revealed no statistically significant differences between the streams among any of the metrics measured, highlighting that despite Richland Creek having a closer proximity to the effects of urbanization, the more rural stream, Little Harpeth, still had similar water quality. The similarity between these 2 streams raises concern for how the effects of urbanization and pollution may be reaching watersheds everywhere. Further, our findings demonstrate the need for more consistent field data collection. Lastly, based on our findings, we recommend that the nearby golf courses invest in the use of organic fertilizer, minimize the alteration of the riparian buffer, and reduce stream water intake for golf course or commercial use. Thank you. We are now happy to accept any questions from the audience.